All right, so why don't we move on to our next speaker, who is Chancellor Johnstone. He's a captain in the United States Air Force and an assistant professor in the Department of Mathematics and Statistics at the Air Force Institute of Technology. He received his PhD in statistics from Iowa State University under Dr. Dan Nettleton, and his current research is focused on uncertainty quantification and optimization under uncertainty. And his favorite sports teams are Manchester United, FC Cincinnati, and the Cleveland Browns. And Chance, which is an excellent name for a statistician, will talk to us today about who would have won the 2020 NCAA basketball tournaments. Chance.
Awesome. Thank you so much, Scott, for that introduction. I'm going to pull up my slides here. Okay. All right. Hopefully everyone can see those.
It's good.
Great. Well, thank you everyone for attending today. I'd just like to echo Nate. That was a very interesting presentation to start off with. So I'm sorry for myself that I have to follow that, but very, very interesting. So today I'm going to talk about specifically and trying to answer the questions of which teams might have won the 2020 NCAA men's and women's basketball tournaments. Okay, so as we know, those tournaments following the 2019 to 2020 season, they were canceled due to COVID. Okay, so kind of during this scenario, we wanted to see, okay, well, what might have happened? So we really wanted to look at one, sort of estimating team strengths for both the men and the women for this particular season, and then use those team strengths to not only assess how good those teams were, but also what their tournament win probabilities were. So really what the probability for each of these teams were to actually win the March Madness, if you will. So the question of interest is, given a collection of games, specifically a collection of games with which we have win probabilities. So we might have a home team and an away team, and we know the win probability for the home team. The question is, can we generate win probabilities for a tournament for each team? And well, this is a question that's been answered in previous work. Really, we just have to consider not only the probabilities of each individual team beating all the other teams, but in a tournament, the probabilities for playing a team in a subsequent round. Okay, so we might want to identify specifically the probability of a team I winning in round J. So this QIJ, well, that entails not only the team of interest winning in the previous round, but also has to do with all of those probabilities associated with all of the other teams that we could play and their probability of winning in the previous round. Okay, so if we can identify all these teams that we could play in these rounds, we can actually look at and identify our own probabilities. So let's just kind of walk through an example for a smaller single elimination team. So we have these 8 teams. We have the highest ranked team, team 1, playing team 8, team 4 playing team 5, 3 versus 6, 2 versus 7. So in the first round, obviously team 1 plays team 8. But in the second round, if we're considering team 1, well, team 1 could play either team 4 or team 5. And then all of that kind of holds in a similar manner for all these other teams. So if we have some collection of probabilities, so for example, team 1 in round 1, they're playing team 8, so they have a 99% probability of winning that game. Team 1 has an 86% chance of beating team 4 and an 86% chance of beating team 5 in this case. Well, using this sort of recursive formula, again, knowing who we can play and their probabilities for winning in previous rounds, we can actually get not only their probability of winning the tournament, but also individual rounds. Okay, so for example, team 1, just because they're only playing team 8 in the first round, has a 99% chance of making it out of that round. Team 1, given that they could play team 4 or team 5, has an 87% chance of winning and moving out of that round, and then has a 60% chance of winning the overall tournament. Okay, so we kind of can do this with the March Madness landscape, okay, knowing that we have sort of a fixed bracket and it's single elimination, and we can really identify and map out who we're playing in later rounds or who we could play in later rounds. The question is, okay, so we still need these probabilities, right? So that was a situation where we knew the probabilities, but what we want to talk about now is, okay, we know the team's playing. and we estimate the margin of victory. And by margin of victory, we mean the difference between the home team score and the away team score. Well, we really use a simple approach to do this. We basically use what we call, or what is called, what has been traditionally called the Harville Method. So the idea is we have some margin of victory that we observe. So for team I at home against team J, the margin of victory is MIJ. We have a home field advantage H. We have some team strength. So for team I, we would call the team strength SI. And we have some random unobserved error that is associated with this. So we kind of have the team strengths and this home field advantage, but there's some randomness associated with the actual margins of victory that we observe. So the goal really is to find values of H, SI that really match our observed margins of victories the best. Okay, so as an example, we might have 4 teams, teams 1 through 4. Well, this is the first 3 weeks of the season, and this is all the information we see. So in the first week, the home team, team 3, beats the away team, team 1, by 5 points. Also in the first week, team 4 at home loses to team 2 by 7. So we have a negative margin of victory. So really, we want to take this information and generate estimates of these parameters. We want to find an estimated home field advantage, an estimated strength for team 1, team 2, team 3, team 4. Okay, so we do this using the Harville method, and that allows us to get to actual estimates of team strength. Okay, so specifically, we do this through just straightforward linear regression. Okay, so we can have, for this particular example, we have an estimated home field advantage, an estimated strength for team 1 all the way to team 4. So if we wanted to know what our expected margin of victory was for, say, team 1 at home against team 2, well, we would take 5.75, we would subtract 6.125, and we would also subtract 9.375. And that would give us our estimates for that particular matchup from a margin of victory perspective. So now the question is, how do we go from this margin of victory to win probabilities? So I kind of skipped forward a little bit ahead, so I apologize. We did this for the regular season. So we did this for 2019 to 2020. We got all of the data, the margins of victory, who was playing who, at home, away, neutral, and we estimated these team strengths. So for the men, the estimated team strengths are off to the left. For the women, the estimated team strengths are off to the right. So we can see that Kansas in our analysis seemed to be the highest or the strongest team. And that was kind of consistent across our rankings and other rankings. So we have the AP poll at the end of the season or before the season was canceled, net ranking and Ken Palm. Off to the right for the women's, it seemed that UConn was the strongest team. But there seemed be a little bit more differentiation as far as the ranking systems. So for example, if you look at Baylor, we ranked them 8th, but AP, RPI, and College Sports Madness had them ranked a little higher. We can also look at Princeton, whom we had ranked 5th, but AP and CSM had them ranked 22nd and 20th, respectively. Okay, so we have all of these team strengths now. And so knowing that we have these team strengths, we can get to an expected margin of victory for that game, but we really don't have probabilities quite yet associated with a win for the home team. We just kind of have what we expect them to win by. So we want to go from these margins of victories to win probabilities, specifically win probabilities associated with these with the home team. So we do this through something that is called conformal prediction. So conformal prediction has been around for about 20 years now, but it's just kind of recently starting to pick up steam over the last 10 years, I'd say. It's an inference methodology that is based off of how well incoming observations, so observations that we haven't seen yet in our margin of victory example, this would be a game that we haven't seen yet. So this would be a game between 2 teams that haven't played. Well, we want to see how well that observation conforms to a previously seen observation, how well it conforms to our training data or data that we have observed. So in order to really talk about how well or the sort of how probable we think a potential margin of victory is, we kind of follow these steps. So first, we have to pick a hypothesized response value. So we pick a margin of victory that we're interested in testing to see how probable this margin of victory is with respect to all of the other results we've seen. So for this new observations, a game we haven't seen before, we really assign it a hypothesized value. So for example, we might assign it a margin of victory of -25. Well, we take this new observation and we actually retrain our model with this new observation in addition to the original training data. Okay, so we kind of use it as a data point. Even though we haven't observed it, we use this hypothesized observation as a data point. Then we can retrain our model. Following the retraining of the model, we actually calculate conformity scores for each observation. So for each observation, including the incoming observation that we really don't know anything about, we're hypothesizing a value on, we calculate this conformity score and we can see how different the conformity score is from other observations. So observations that have conformity scores that are sort of similar to other conformity scores we see, we might sort of attach more probability to that observation, or we would see that as more probable than, say, a conformity score that is drastically different from other conformity scores associated with our other observations. So really, we can do this for each hypothesized value to really get an idea of how probable each hypothesized value is. So we can, this is useful in a lot of settings for in uncertainty quantification to really generate prediction intervals around a predicted response value. So we might use these to actually use conformal prediction to construct these intervals around a certain prediction point. So what does this look like? Well, say we have 3 hypothesized values. Well, when we use those hypothesized values, we take the individual observation of interest, we attach our new hypothesized value, we retrain the model, and we construct conformity scores. Well, our conformity scores might be the residual between our prediction and the observed value. So we can compare the conformity score associated with a specific hypothesized value to all the other conformity scores. So off to the left, we have a particular hypothesized value of the margin of victory of 25. Well, in this particular scenario, knowing that the histogram shows sort of where the rest of our conformity scores, the rest of our observations lie, we can kind of see, well, it's kind of different, but not that different. It's kind of on the tail, but not so far on the tail that it's not probable. Off to the right, we have a situation where the hypothesized value is 40, I believe, in this example. So we can see that this hypothesized value, the conformity score associated with the observation with this hypothesized value is very different from our other conformity scores. It's way off, very far in the tail, or the right tail, if you will. We can also look down at this middle example and see, well, for this particular example, and this is a hypothesized value for this particular game of 0, we can see, well, the margin of victory 0 has a conformity score that's really kind of in the middle of all of these observations or all of these conformity scores. So we would kind of assign this margin of victory sort of a high, we would say this is very probable. Okay, so in the sense of assigning probability now, we can really just take the number of conformity scores on the one side or the other of our particular conformity score. And then that is a probability associated with specifically exceeding or being less than that particular candidate value. So knowing this, we can actually show probabilities for specific games or get estimates of probabilities for specific games by just sort of testing a bunch of different possible margins of victory. So what this looks like from a probabilistic perspective is, for example, let's suppose our game of interest is we want to see or assess probabilities associated with Connecticut versus South Carolina. Well, we could see, and we can actually look at, and off to the left is our, we're saying that this is an estimated probability that the margin of victory M is greater than some hypothesized value M, or some candidate value M. So really, this is our random variable margin of victory, and we're estimating the probability that this random variable margin of victory is greater than this M value. So this really is describing a win, specifically at a specific instance. So if we select this M equal to 0, that is a probability of a win in this particular game. As far as Connecticut versus South Carolina, we can see that the probability that Connecticut does not lose by over 40 points is very high. Okay, off to the right, we can see that the probability that they win by over 40 points is very low. And then we kind of have more reasonable probabilities as we get closer to 0. South Carolina, in this instance, if we go back to this figure, they were the second ranked team for the women's. Arizona was the 10th ranked team, and Dayton is very far down, but I'm actually in Dayton, Ohio right now. So I had to rep the University of Dayton. But we can use this approach to get probabilities for specific games. Okay, so any game that we want, we could basically check all of these hypothesized values to get win probabilities. And so specifically, we really only need to capture or check 0 as a win probability, or for our win probabilities. We can also look at other ways, and so we compare to these other ways of generating win probabilities. The first is we could use linear regression, so the same prediction method that we actually use, but we make normality assumptions. So our method, the conformal prediction method, makes no assumptions about normality. So this is kind of assuming some stronger results. Well, the estimated probability that the margin of victory for home team I against team J greater than 0, we can actually sort of reduce this to 1 minus the probability of being less than negative m hat, so our predicted margin of victory for home team I against J, over some prediction error standard deviation. So when we sort of make these adjustments, we can actually just look at the CDF associated with a t distribution with n minus p degrees of freedom, where p is the number of teams in this case. We can also use logistic regression, which is a slightly different method for estimating probabilities. And instead of focusing on the difference in margin of victory, we actually are estimating the log odds of victory for a particular matchup. So then, knowing that we have the estimated log odds, we can do some sort of transformation to actually get to this win probability. Okay. So these are the methods we compare against. And we'll kind of show results here at the end with respect to the conformal approach, the linear approach, and the logistic approach. So we'll kind of get into the specifics of March Madness now. So following cancellation, there were 20 unfinished men's conference tournaments and 18 unfinished women's conference tournaments. Okay. So what that means is there wasn't a set collection of teams that had made the tournament. This kind of results in 5 different situations that teams could fall into, and I'll get into that in 2 slides. But really, it also, it doesn't allow us to calculate these tournament probabilities because we don't know the actual teams that were in the tournament. Okay, so we can't use our recursive approach to generating these probabilities. We also simplify our bracket generation. So knowing that the selection process is sometimes or a lot of times a subjective process and not really formulaic, we had to sort of simplify the generation of the bracket. So we do that using an S-curve method. The S-curve method, we kind of show it here, but really it's not used in selection. It's more used to just kind of break teams into different tiers rather than placing them in actual regions. But the S-curve method in general is used to sort of make the strength of the collective number of teams in each region equal or as close as possible. So we sort of have this snake approach as far as the overall ranks and where we place these teams. So we go, just team 1 is placed in region 1, team 2 in region 2, 3 in region 4, 4 in region 5, but then we snake back down. So we put 5 in region 4, 6 in region 3, so on and so forth. So we're kind of making this snake pattern. So that's what we use to actually assign teams to specific seeds in the tournament. Okay. These are the 5 situations that kind of happen with the cancellation of these conference tournaments. Either a team has already made the tournament, so they have already won a conference tournament, or they are ranked so high that it is impossible for them to not be an at-large bid into the conference, or into the tournament. So the tournament has automatic bids, people that win their conference tournaments, and at-large bids, teams that don't win their conference tournaments but are good enough with respect to the rest of the teams to be invited to the tournament. Situation 2, a team must win their conference tournament, or they rely on a lower number of teams to make the tournament so that they get an at-large bid. Teams can rely on just a small number of teams ranked below them to make the tournament. The 4th situation, they must win their conference tournament, or a team cannot make the tournament. So they have not won their, or could not win their conference tournament because it's already happened and they lost, and they were just low ranked that they would never have expected to get an at-large bid to the tournament. So we can kind of look at the women's side and we can organize these teams into these 5 situations. So specifically for the women's, there were actually no teams in situation 2. So there are no teams that could win their conference tournament or rely on a small number of teams ranked below them to win. It was either you won your conference tournament or there was enough teams ranked below you that won that you got in as an at-large bid, specifically at the point where these conference tournaments were canceled. Well, we can actually use our conformal approach to assign win probabilities for all these potential matchups that were remaining in all of these conference tournaments. So we assigned these probabilities with conformal prediction and actually assigned probabilities for all these teams to either win their conference tournament or get into the tournament as an at-large bid. So that is a part of the discussion that I won't talk about in here, but it was kind of a grueling calculation. But really we can see that for each of these teams, say in situation 3 and situation 4, they all have these probabilities associated with making the tournament. Yale, for example, who is a relatively high ranking team that didn't win their tournament, but was relying on lower ranked teams to win, had a very high probability for making the tournament. St. John's in a similar position had a very low ranking or low probability of winning. We can go off to situation 4, which is they must win their conference tournament. We have these probabilities. So one interesting thing that we identify is that we have Oklahoma and West Virginia who are in the same conference. One is ranked above the other, but their probabilities don't align with that ranking. So West Virginia was actually seated ahead of Oklahoma in this conference tournament, and they had a bye. So they have a little bit higher probability of winning, even though they are technically not as good a team as Oklahoma from our strength assessment. We also looked at obviously the tournament win probabilities. So the interesting, or the problem with this kind of reared its ugly head again is we could look at the probabilities associated with winning the conference tournament, and we could look at probabilities for winning the tournament. But the difference was we're still missing where these teams were seated. Okay, so knowing that we couldn't actually identify the selection process for seeding a team, we used this snake method to seed teams. Okay, so this was we generated a tournament bracket that was filled by teams that were selected as the highest probability of winning their conference tournament. So we selected winners of the conference tournament as teams that had that highest probability. We built a bracket off of that, and then we constructed probabilities associated with that bracket. So for this, we could actually see that Connecticut had about a 29% chance of winning. South Carolina had a 12% chance. Stanford had a 0.1% chance. And this is specific to the women's game. So we have some backup slides for men if anyone's interested, but the paper discusses from the women's tournament perspective. So again, this is particularly generated with conformal prediction, the conformal prediction approach. Okay, we actually generated a lot of different brackets. Okay, so this was particularly filled by the highest probability for conference tournaments, but we constructed a bunch of other brackets, and it turns out that these win probabilities for the tournament really don't vary much regardless of the bracket, just because the teams that are strongest are in the tournament regardless, okay, because they'll either win their conference tournament or they will be an at-large bid because they're so high ranked. So these probabilities, regardless of the bracket, as long as it's a reasonably constructed bracket, they don't change very much. So these are about, kind of what we saw similar across many different brackets. So we wanted to look at and say, okay, now these probabilities that we generate using conformal prediction, we wanted to compare that method to the linear regression method and the logistic regression method. And ideally, ours would perform better. Okay, well, we actually looked at and we wanted to see how well our methods were calibrated, or our method was calibrated. Now, calibrated means, for example, if we predict a team to win a particular game with a 40% probability, well, we should, out of all the games that we predict with 40% probability, about 40% of them, they should win. So we should be aligned with sort of these probabilities that we construct. Well, we did this for compared calibration for the men and the women. And I'm sorry if I'm going over time. Can I get a time hack real quick?
Yes, if you could.
I'm sorry, Scott, I didn't hear how much time you gave me.
Perhaps you could finish up in 2 to 3 minutes.
2 to 3 minutes. Got it. Thank you. So we can see the calibration. So we sort of look at all these probabilities and we bin them depending on what we estimate And it may not be apparent here, but actually the conformal prediction method is much more calibrated than these other two methods. Okay, you can see we kind of have some issues with the women's where we have some calibration issues around the sort of 0.15 and 0.25 region. It's important to note that these particular probabilities here, it included like 5 games and we just happened to get a majority of them wrong. But as far as other loss measures are concerned, we can see that conformal prediction or using conformal prediction to generate these win probabilities is actually very competitive, in a lot of cases better than the linear approach to the logistic approach. So when we use a specific loss function, the expected calibration, so we kind of average our overall calibration, well, conformal is better in a lot of seasons than except just one. And when we use an alternate calibration loss, which looks at the overall worst calibrated point across all our observations, linear is much better, at least for the men, at least for, excuse me, the men, I think I have the tables messed up here. The men are on top and the women are on, the women's results are on bottom here. But either way, we can see conformal actually is pretty competitive compared to these other methods. And so this was testing, we took the regular season and we took and tested it against the postseason. So we generated strengths with regular season, and then we generated win probabilities for all the games in the postseason, which includes the conference tournaments and the Division I tournament, if that existed in that particular season. Okay, so overall, we performed pretty well. So this just kind of gives us a way forward for generating these win probabilities that we haven't seen before, and that is really competitive to other methods of generating win probability. So some issues with this analysis, one is just related to data. There was inconsistencies related to both the men and the women's data. In particular, the women's data was much harder to find, one, and difficult to obtain, and difficult to clean. What I found was just the men's data was just readily available. The women's data, I actually had to go to NCAA.com and scrape all of the data across those years to get the data and actually utilize for the analysis. As far as issues with the model, well, what don't we account for? Well, we're just doing, it's basically average team strength across the season. And that's what we use to generate these win probabilities. So it doesn't account for how well a team is playing at the current moment. It's an average. It doesn't account for injuries. So how does a star player, or how does a coach not being around, how does that affect the team strength? We don't account for that. Also, we don't account for matchups. So maybe one team is particularly suited to beat another team, even though that team is very, very strong. So we do not account for that. That's something that we think can be implemented and utilized in previous or future work. So we would like to hit that. We also oversimplify the bracket generation process. So we identified that, okay, the bracket really doesn't matter. The probabilities are the same for the most part. But it would be interesting, and even though difficult, to sort of get this selection process actually implemented to talk about these probabilities. We also double dip on team strength. So we not only use them to generate probabilities, but we also use them to seed the teams. So we're kind of using that twice, if you will. Future work, we'd like to maybe utilize more complex modeling approaches. So we just use linear regression in this case. But we'd also like to extend to maybe a fuse lasso approach, which gets into teams maybe getting better over a season or worse. We'd also like to apply this to betting scenarios. Specifically, when we use this conformal prediction approach, we can look at different things rather than just win probability. So we could assess spread probability and go that direction. We'd also like to extend to other leagues, whether that be professional or amateur. This sort of process is, applicable to any number of sports where you have a margin of victory. Okay, so that's all I have. So any questions would be welcome. And here's a subset of the references that we use.
All right. Well, thank you very much, Chance. That was excellent. Interesting stuff. Why don't we take one question before we move on to our next set of speakers? If you want to place a question in chat, or
While people are typing their question, I can ask a really quick one.
Okay.
Chance, so nice job. Had you considered at all doing something like Bayesian modeling, and then once you get future outcomes, you can just simply use the posterior predictive distribution of future games to actually measure the probability, which is, a fairly standard approach to take. So I'm just curious if you thought about that.
So that has been a part of the conversation. I think this research project it's in its like fourth iteration now. We kind of keep trying to do new things or keep adjusting it. So this is hopefully the last iteration of my PhD work, but definitely an alternate approach as far as, using Bayesian approach is definitely within the realm of possibility. We've also discussed using sort of a Bayesian approach to sort of get at the idea that margins of victory are integer, right? So that's kind of something when we do our analysis, we kind of assume away that restriction and we kind of work on this continuous realm for the margin of victory. So we've often discussed, hey, how do we get at this integer piece? So not with respect to the probabilities, but definitely with respect to sort of this integer issue for margins of victory. Good question. Thank you very much.
All right, thank you. I don't think we have further question. Oh, one last question just came up.
Yes. So as far as home advantage,
You should probably read here. You should read it just because not everybody's looking at it.
I'm sorry. Yeah. So thank you, Barbara, for the question. Perhaps I missed it, but does the home field advantage disappear from the picture because the tournaments are neutral? Yes. So we still estimate that home field advantage using this, using the regular season data. But when we go to the tournament, we assume no home field advantage, which maybe not necessarily be true, given that I think traditionally there is some aspect of location with respect to who's playing where, but we do remove that home field advantage, but we still use the same estimated team strengths that we generated, assuming that there could be a potential home field advantage. Thank you for the question.
Right. All right, great. Well, thank you, Chance. That was very interesting